Yes, so my name's Stuart Chalk. I'm a technical editor of the IUPAC Gold Book. I'm also a co-chair of the Joint Subcommittee on the IUPAC Gold Book, the JSIGB, and a titular member of CPCDS, the Committee on Publications and Cheminformatics Data Standards. And thanks to both Oliver and Philip and the other organizers for giving me time to speak about the Gold Book. So what I'm going to do is give you a very quick introduction to what the Gold Book is and how IUPAC is looking at this relative to the important area of the semantic representation of chemistry. So if you haven't been to the website, this is kind of an overall snapshot of the different pieces and what it looks like. The site has just under 6,500 concepts in chemistry defined. And as you see there in the bottom left, each one of those concepts has been assigned a DOI. There's also provenance of where the definitions come from, and I'll talk about that a bit more as I get into this. And then finally, in this iteration of the website, which was launched in 2019, there is also an API, which means, of course, you can call the API and get the data via code or via some machine accessible route. One of the things that we're interested in doing is, as we move forward with the Gold Book, is developing processes and practices to ensure that the definitions that are in the Gold Book are born digital. And it'll become apparent why that's an important activity in a second here. But relative to this particular workshop, we thought right up front it would be good to kind of make sure that we talked about why we are interested in this activity and how we want to support it. Obviously, the Gold Book is about defining chemical concepts, and ontologies, of course, are a way to represent the semantics of a domain knowledge. And so these two things fit together very well. So we want to help enable the semantic chemistry community in any way that we can through the Gold Book. And then that means to us, we're supporting chemistry-related ontologies, enabling machine processable meaning of chemical information, and importantly, to use the Gold Book terms to define the meaning and allow reference to the meaning of chemical concepts via DOIs. So one of the things we thought about was, well, what can we say here about what we would like to do in terms of collaborating with this community? And so the API, which I'll show you in a second here, exposes some metadata about the individual chemical concepts that are in the Gold Book, but maybe this community would look at that and say we can do different things with that, or can better support machine processable meaning in that context. We also thought it would be really good to develop a mechanism where a Gold Book concept, if it can and is utilized in an ontology, that it can also be exposed back on the appropriate Gold Book page, kind of making sure that there's a two-way communication of the information. Also, clearly, one of the big topics I think we're going to talk about in this workshop is coverage of ontologies and therefore gaps in terminology or concepts. And that's actually something we're very interested in terms of the definition of these terms. So engaging the community to be able to help us find where those gaps are. And then also encourage anybody here or other ontology developers to join IUPAC projects on the definition of the concepts, so that we, IUPAC, can move towards a more agile concept definition authoring pipeline. So in the essence of time, let me quickly just give you a very, very quick snapshot of how this all works. IUPAC publishes formal recommendations, and not all, but most of those recommendations contain terminology. And those terms are therefore, they go through the formal process, and they are authoritative definitions of these different terms for chemistry. Here's a couple of examples of terms from a very recent update to the glossary of terms in physical organic chemistry. You can see there's a definition, there are additional notes, there's provenance in terms of citing original sources, and related terms to the term that's defined. We have in the link on the left-hand side guidelines for writing a concept definition, which is quite detailed and actually is undergoing a slight revision as we speak. So these concepts have been integrated from the PAC recommendations, have been integrated into an online thing called the Gold Book. Originally, that was a physical book, but as of 2006, there was a website. And as I mentioned, in 2019, the website was redeveloped, and we now have something that is very much more appropriate for today's technology. It's device agnostic. As I mentioned, it has an API. There's a download of the vocabulary. There is a GitHub repository in support of the project. And most importantly, all of the terms are licensed CC BY NC ND to try and make sure that they are fair for the chemistry community. On the right here, you can see some statistics. There's a lot of different terms, obviously, across the different divisions of IUPAC, and a lot of references to the terms in Wikipedia, and as you can see here, entries on Wikidata. This is what the current Gold Book website looks like. It's basically a much nicer interface to the definitions. It uses common and more recent technology to be able to do the website development. It's all database driven. And at the bottom there, you'll see a little icon that says JSON, and that's how people can access the API, which looks like this. We make the data available via the API in both XML and JSON. And there is also metadata available for each of these terms. If you go through the Crossref API, which was that metadata was recently updated last year to more accurately represent the provenance of where the concepts came. Currently, we are in a huge process of updating the Gold Book content. The 2019 renovation of the website was only that. It was only a renovation of the actual presentation of the material, the definitions. It was not a definition update, and that's what we're going through now. So what you see here is a new website that I've built to facilitate the aggregation of and the processing of definitions that are of more recent PAC recommendations. The existing content is from older recommendations, and there's obviously been a lot of work done in defining and redefining terms in the interim time period. So we have a lot of work to do to go through the process of taking the new recommendations, digitizing them correctly to put them into the Gold Book website, and going through the process of making sure they are checked as we do that. Where we are with this process is we've tested out, we're testing out right now this TRS, this term review system. We have one particular recommendation in analytical chemistry. There's over 100 terms in chemometrics that will probably be newly available on the Gold Book website somewhere in the November timeframe of this year. Like I said, we're working through the mechanics of the process at this moment, and there are other recommendations that are coming through the system, which we hope are going to be available by the end of the year. They include the Orange Book on analytical chemistry, which has over 3,000 terms. As I mentioned, the Glossary of Physical Organic Chemistry, 700 terms, and that's, by the way, the fourth iteration of that glossary. We will put in not only the new version, but also make sure we link the previous versions of those terms. So there's actually the provenance of the term evolution, not just the provenance of where they derived from in the literature. The goal is for us to try and complete this activity by the end of 2023. And that means that I anticipate at that point, the Gold Book website will contain somewhere close to 12,000 defined concepts in chemistry. Obviously it's going to be a much bigger website, and because the content is updated, it's going to be much more appropriate. I've included in these slides, which I will make available, of course, here are the individual divisional projects for the update process, so that if anybody listening in is interested in joining this activity, you can go along and go to the project and then contact the project chair to get in on the actual project's activities. And as I said, we're here to try and support the chemistry community with definitions of chemical concepts. And so we invite collaboration. I'm excited to hear your questions. And if you don't get to your question in the small period of time we have after this presentation, please reach out to me in the chat or Leah McEwen, who's on the call as well. We'll be happy to answer questions about the Gold Book. There's my contact information. If you want to send questions to us via the Gold Book's email address, it's there, goldbook@iupac.org. And I just wanted to point out that this is not a standalone thing. So there's lots of people involved in this activity. The other editor of the Gold Book is the Jan Kaiser, who's the content editor, and then the conveners of the joint subcommittee that is focusing on how we go up and update the Gold Book, but also what its scope is and what its support for use cases are. Those are Jürgen Stoner of ICTNS and IUPAC, and Leah McEwen, as I said, who's on the call from CPCBS. Thank you, and I hope I haven't run out of time.
So I'm Adnan. I work as a chemistry database creator for the ChEBI database at EBI. So in this talk, I'm just going to give you a brief introduction to what ChEBI is and also what our future plans are going forward. So ChEBI is a manually annotated database. It's an open access database of chemical entities of biological interest. So these chemical entities may either be natural products or even synthetic compounds such as drugs. The database currently contains 159,000 entries, of which around 60,000 of these have been manually annotated by the ChEBI team. So what does ChEBI actually provide? So for a given chemical entity, so here's an example, a nicotine, S-nicotine. It's an alkaloid found in tobacco. So for a specific chemical entity, we'll provide a 2D structure, and if a 3D structure is available, we'll provide that. And we'll provide an unambiguous ChEBI name for that structure, and also we'll assign a unique and stable identifier for that specific entry. In addition to that, we'll provide a range of properties, formula, charge, mass, and also a list of identifiers, INCHI, INCHI-key, and SMILES. We'll also provide a comprehensive list of chemical nomenclature. For example, we'll generate an IUPAC name for the structure, and also, especially for pharmaceutical drugs, we'll also provide international non-proprietary names in several different languages, along with synonyms. So these could be either systematic names or traditional names of chemicals, or even research codes, and also trade names. ChEBI also provides an ontological classification. So we classify chemicals based on the chemical classes they belong to and also the biological roles they exhibit. For natural products, we also provide species data. For example, if a natural product has been isolated from a specific organism, we'll provide the name of the species where the chemical has been isolated from, with a link to an appropriate taxonomy for that species, and also evidence from where we got this data from. ChEBI also provides a list of citations where, for example, publications which mention the entity is provided along with a link to the full article. And we also provide database cross-reference links to around 68 different resources. So some of these are mentioned here. And we also provide registry numbers to CAS and REACCESS. So how is ChEBI used? So ChEBI is actually widely used as a small molecule reference database by a number of resources. And it's quite also widely used by the ontology community, especially gene ontology, to handle the chemistry-related terms. So where does the data come from in ChEBI? So there's actually three routes how data gets into ChEBI. So one is individual requests. So we have individual users from either academic institutes or even pharma companies who are submitting data to ChEBI via ChEBI submission tool. The other way is we have some major users who are constantly submitting data to ChEBI. So our major users are RIA and metabolites. So RIA is a biochemical reaction database at the Swiss Institute of Bioinformatics, and metabolites is a metabolomics repository based at the EBI. So these two databases are submitting thousands of compounds every year to the ChEBI database. And then once in a while, we also do sometimes preliminary loading of data from other resources. For example, in the past, we loaded a subset of compounds from HMDB or CHEMC. So what is the ChEBI ontology? So the ChEBI ontology is just a structured classification of entities within ChEBI. So it's actually subdivided into 3 different sub-ontologies. So we have a subatomic particle ontology, which classifies entities that are smaller than that are particles, for example, your electrons, neutrons, and protons. And then you have a molecular structure ontology, which is designated here as chemical entity. So here we classify chemicals based on the chemical classes or chemical composition of the structure. So here, entities can be classified as hydrocarbons or carboxylic acids and so on. And then we also have a role ontology where we classify chemicals based on the function of the molecule. And these can then be further subdivided. For example, a role can be subdivided into a chemical role or biological or even an application. So an application is the use of a chemical entity by a human. For example, is it being used as a drug or is it being used as a pesticide? So these chemical classes can be further subdivided into more specific classes. For example, chemical entity is subdivided into a molecular entity and group. ChEBI also contains groups and residues, maybe certain parts of molecular entities. We also include that in the database, because some biologists may be interested in what a carboxy group is or what a methyl group is. So we have these type of entities as well. The molecular entity branch can also be subdivided into or inorganic and organic. So, for example, sodium chloride is a member of inorganic molecular entity. And then, but the vast majority of chemicals in ChEBI are organic in nature. So, for example, S-nicotine, we'll classify this as into a more specific class called pyridine alkaloid. So just by looking at this chemical structure, we'll be able to see what the type of class it will belong to. But the ontology is actually more complex than this. Here, I'm just showing a single is-a-parent relationship, but some of these chemical entities will have multiple is-a relationships. But a chemical entity may also have some sort of function. For example, S-nicotine has role as an anxiolytic drug. And here we actually link the chemical entities not only to the molecular structure ontology of ChEBI, but also to the role ontology. But we also have at least 8 different chemistry-specific ontology relationships in ChEBI as well. So when you have thousands of molecules classified within the ChEBI ontology, you can carry out some really complex queries. So we have this advanced search built into the ChEBI public website, which allows you not only to do some simple structure-based searches or text-based queries. For example, if you want to search for identifiers or if you want to search for synonyms, but you can also do some very advanced searches or combine your searches with these Boolean operators and or but not. So you can also query the ontology. You can find, for example, one can find all steroids within the database that are also plant metabolites. And you can also carry out searches like, for example, find all thiazoles that has role as antineoplastic agents, because we've already classified a lot of these chemicals into their respective classes. So, our future, one of the future goals of it, because some of you may know ChEBI is quite an old ontology. It's 18 years old. It was developed in 2004. So its infrastructure is pretty slightly outdated. So we just recently applied to the BBSRC and we've just been awarded a 3-year grant. So this is slightly an ambitious project. We're trying to redevelop the entire infrastructure, the back end and the front end. So the ChEBI actually will be developed using a slightly more modernized tech stack, because we recently developed Chemble, so it's going to be built on the same software stack as Chemble and other chemistry resources at the EBI. We're going to actually rebuild the creation tool as well as the submissions tool, so it can be slightly more streamlined, because it's a tedious process at the moment of people have to add data step by step, and it just becomes a long process. We're going to actually also improve the web services, and we're going to simplify the current ChEBI database schema. And there are some we're going to also move from commercial software to open source software. And here are some of the individuals involved in ChEBI's development over the past 18 years. And thank you for listening.
So the Chemical Information Ontology is what I will present here. This is the paper from 2011. There are too many slides to cover in 7 minutes, so I will go through it, but I will give the link in the document. And the Chemical Information Ontology is, well, as it describes here, to write down the provenance, the ambiguation of chemical data and yeah, some of the use cases were the biological context, but really the use in the semantic web. We needed ways to indicate that something was a SMILES, for example, or something was an INCHI. But we actually went beyond that because we realized that SMILES is not any SMILES. So SMILES is a concept, and it's not really a very accurate descriptor of some chemical information about the chemicals. So this descriptor describing something. And it actually is an algorithm that describes how you get to a descriptor, particularly in the case of the SMILES and of an INCHI, but also in case of IUPAC names, for example. And the algorithm itself is one thing, but you might have one algorithm with multiple implementations in different software libraries, all things that we wanted to express so that you could say, well, this INCHI is actually calculated with INCHI library 1.06 instead of 1.03 from a couple of years ago. And likewise other things. So we needed that, for example, in the chemistry development kit, our open source cheminformatics library, where we had a lot of descriptors calculated, and we wanted to formally describe those descriptors and also to link them in that way, in a machine readable way, to the literature describing those things. Now here we see an example in semantic web in turtle format of how you would actually give a value, and you see the ChEMINF ontology being used here along with the RDFS, the RDF schema ontology, and also the CO ontology for giving a value for one descriptor. And one descriptor here is the entry ChEMINF 000405. So yeah, you'll immediately see here that yeah, with these machine readable identifiers for terms in the ontology, you really need the ontology itself to look up the names to make this readable. But there are good reasons for doing that, which I won't go into. So I mentioned the use in the chemistry development kit, annotating the software implementations, and that is what we see here. So up here we have a bit of Groovy or Java code, almost Java code, using the chemistry development kit, asking for this total polar surface area descriptor for that molecule. What was calculating it? When was it? What was the reference? The reference for that at sorts. So that gives you information about the provenance, something that we needed to make QSAR modeling more reproducible, for example. And then the output would look something like down here. Code there is in the CDK book actually. Now, and the use cases of this ontology, and we'll see a bit more about the ChEMINF ontology there, is for example, in how we share nanosafety data. Nanosafety data is safety toxicology data for nanomaterials. And for nanomaterials, we have the same kind of things. They're chemicals, so we have chemical descriptors or substance descriptors describing some property of the chemical. And that is more explained more in the paper about the inanimate ontology. And if we look at the structure of that, you actually see the ChEMINF ontology somewhere just above the middle there mentioned for describing the chemical descriptors. Also here the ChEBI ontology that we just had in the previous presentation, and some of the other the OBI, BFO, and the IAO that we saw mentioned earlier. So that gets us to the question of how are these things imported. So InanaMapper does that in one way. ChEMINF actually does it in another way. And we'll see that in a second. ChEMINF actually is based on the basic formal ontology. The 1/2, not a half, here actually refers to when the article was published 11 years ago. There was basic formal ontology 1. So that comment that we saw earlier about splitting the BFO1 into BFO2 and the relational ontology actually applies here. And it looks like we may have ironed out all the changes, but somewhere last year someone reported that there were still some problems left, but I hope we have those worked out. And here you see some of the hierarchy with the continuant that was also mentioned in the opening. Another example of the use case is PubChem. That article was also published some time ago, and there the ChEMINF ontology is also used to describe information about the chemical compounds. So the chemical compounds here in the middle, again the SIO also being used here, and the ChEMINF ontology to describe bits of the information in the PubChem knowledge base in the RDF in the semantic web representation of that. Now, just a few short words on the ontology development. When the publication, the original publication came out, we were using, I think, Google Code. I'm not sure if that was the name, software platform from Google, but that closed down now 5 years ago. So then we moved to GitHub. So that is where things have been happening since. This is the link to the repository, and we have been receiving their pull request and feature request in the issue tracker. And to give some idea of how much is happening there, we also don't really have funding. We don't have any curator here actually for the ChEMINF, so it's all voluntary work as well. But we do get actually pull requests for the ontology to add terms, and this is actually reflected that over the last 3-4 years we still see some development. I think we moved to GitHub somewhere in 2018, so that's probably that peak here. So we're using the web ontology language as the source. So there is no OBO there. Something about that in a second. So we're using OWL imports to get things together. So this root level OWL file, but it imports actually OWL files as well. And one of the presentations mentioned about copying ontologies instead of importing them. In EDAM, we actually did that better. So in the EDAM ontology came after the ChEMINF ontology, and there we're actually more in a software manner importing ontology. So actually taking the original ontology and getting out the bits that we want. I don't think that is the case here yet, but that is something that we are looking into right now. This slide is the data model for chemical information. So this gives some idea. So at a descriptor level, so how would that be represented here? But I'll leave that for later. A bit too much detail, perhaps for now. So one of the nice things about the ChEMINF ontology, so when it was developed, there are quite a few things there really done at an axiomatic level. So there are some really interesting structures there, taking advantage of OWL axioms, so that you can apply reasoning, so that not everything has to be explicit in the ontology. Something that is useful, which is visible here as well with an OWL equivalent class definition, where we describe here what an atom counting algorithm actually does with the labels down here. Again, I will not go into the details, but 7 minutes doesn't allow that. A last example that I want to show. This is a bit more, well, bit old, bit more recent. So the semantic web representation of the Campbell data, where the ChEMINF ontology has been used as well. So I started using that a long time ago, and that was taken over by the Campbell team. So you have the ChEMINF ontology there to, for example, get out the smiles of a compound. And this I quite like this work from Amar in our group, because he actually uses the CDK depict tool to actually dynamically create this 2D visualization, and the image from a remote from Campbell itself actually is included here as a comparison, but the ones in the last column, that's auto generated from the information that we retrieve with the ChEMINF ontology. Last thing I want to mention is the OBO dashboard. We are looking into that. The ChEMINF is registered there. There is a lot that needs to be done there, but again, we don't have funding. But at least I have a PhD candidate that started, Javi, that started this summer, and his full PhD will be specifically about ontology development. So he's actually now looking at the ontology development kit as well as robot, and see how we can use that for the inanimate ontology, because that's the main target. But we're probably also going to apply this for to ChemInf and the nanoparticle ontology, two of the dependencies of the inanimate ontology. So you can see here, actually last time this was run was at the end of July, and it actually is not entirely correct anymore, because the license information was there, but not in the expected format. So that was one reason why this test was failing. But the other thing actually is that triggered the discussion, and the ChEMINF ontology has changed the license, is now CC0. The versioning thing here flagged that I'm not entirely sure yet how I want to solve that. So that is an open task. So yeah, regarding robots and the ODK, the summary for the rest is pretty clear, I guess. That is something that we're exploring, and we're now actually looking whether we want to use, whether we can use a robot and the ODK directly, whether we understand those tools enough, or whether we help, or maybe does not have all the functionality that we were looking for, but those things are things that we're exploring right now. So an ontology community like this, where these things can easily be discussed, and we can exchange experience in the tricks of the trade, if you like, are very welcome. And that was my last slide.
Hello, everybody. This is terribly exciting. I'll tell you why. We've only got 7 minutes or so. So here is a very quick overview of what's going on. But two screens. Right, there's a quick overview of what's going on. And part of the reason why this is so exciting is that I started work on this 16 years ago. And it is really gratifying to see people making use of stuff that me and my colleagues did quite some time ago, and that we're getting useful feedback, even though this was originally intended for a completely different project, which was to do with text mining, which was a collaboration with the University of Cambridge. And I'm pleased to say that the postdoc who was working on that at the time, Peter Corbett, who many of you will remember, is working at the Royal Society of Chemistry now in our data science team, and doing interesting stuff with patents and publications, and how ideas get transferred from academia to industry, and how that relates into impact. So there's a big longer term project that I'm sure we'll be talking about in the years to come. How did we evaluate whether the ontologies were working? It was partly on whether they were being used, which they weren't hugely being used at the time, and partly on a nebulous thing, which was impact. So we did get involved with things like the Open Facts project, which Echon showed some of the RDF from earlier. So the big ontology that we ended up building was the Chemical Methods Ontology. You can read at your own leisure what it's for. It was kind of because there was a lot of process around OB, and we wanted something that we could use kind of straight away. So we were possibly a bit naughty. This is something I will come back to later. The methodology was the IUPAC Orange Book contains quite a lot of definitions. It is not quite as Aristotelian as a Gold Book. The Gold Book's rather lovely from that point of view. I refer you back to my cover image of Raphael's The School of Athens. We used Excel for building up the ontology originally. This is still a popular tool for building ontologies. And we're showing our age. We used Perl to convert that to OBO format. I'm sure we would use Python nowadays. And I remember OBOEdit. I rather liked OBOEdit. We're all expected to use Protégé now, which is good too. What's not in scope from this? Computational and theoretical methods, which are to a great extent covered by ChEMINF, but there's also computational methods, which I'm sure we'll hear about elsewhere. Now, there's all sorts of things you could do. There's definitely things that you mustn't do. One of them is NMR pulse sequences. So one completely computable way of describing a given pulse sequence would be just to store the pulse sequence in the ontology. This strikes us as a bad idea. You do not want to be feeding stuff from an ontology into a big bit of expensive kit with a big magnet. So let's ensure that nobody does that by just referring people to the literature, so that people who know what they're doing can do what they're doing. Those are the relations that we developed, and these I'm sure we ought to align with the relation ontology. And this has been taken up by NFDI for chemistry. The other smaller one, but a limited one in its scope, is if you are an organic chemist, you spend your first year learning at university, learning about named reactions, which some of them are named after people who are still alive, like the Japanese people who worked on metal catalysis. So this is really nice for text mining, because you're not going to see things like Kanetsaro or Hiyama unless they are actually referring to that sort of experiment. What we classify things on is what people mean to do with the reaction, what they're trying to achieve, because it turns out if you probe how reactions actually work, it's often quite sensitive to conditions, and we've only really learned this properly in the last few years with flow chemistry and things. We have a beast. This is our documentation. This is a flow chart that we use. It's a very limited domain we're working in. These are, standard categories that organic chemists came up with, getting on for 100 years ago. Once the rest of us had persuaded organic chemists of the existence of atoms. So once they'd accepted the atomic theory, they came up with this. People like Ingold. And there are a few bespoke things like protection reactions and borrowing achieves planned objectives from OB. And this is a bit of a colourful diagram of the Diels-Alder reaction, which Roger Sale will point out to you. Everybody studies as an undergraduate. Nobody actually uses in practice. The pale blue ones are RXNO. The dark blue ones are the Molecular Process Ontology. This is something that we need to align better with chemical processes. And the yellow ones here are things from other open biomedical ontologies, such as ChEBI and Buffo, which I'm not sure is an open ontology, and I'm not entirely sure what's happening with at the moment, even though I'm on the mailing list. I may be not alone in this. So yes, NFDI4Chem have been using this. It's on Wikipedia. Next Move Software have been using it, and we have anecdotal evidence of people using it, and good, inside Big Pharma. So things to do. ODK, yes, we would like to use the ODK. My workflow is not a happy workflow. It involves a text editor, so we'd like to do that better. Chris Mungall's excellent blog is not something I spend enough time reading and applying. There are I'm quite sure examples of over-axiomatization and other bad things. Philip and colleagues have found a few things in there that we have already sorted out. I'm sure there are more howlers. There are definitely things in CHMO that should be an OB. And as for interactions with other ontologies, there will be a hands-on workshop tomorrow afternoon, which I hope some of you will take part in. There are questions have come up about how to import classes from ChEBI. And also our interactions with ChIRO and ChEMROF, which I am very excited to hear about from Chris and Charlie. And there's a dangling problem about what we do with fix and rex, which are unloved and which we should have loved more at the time and worked harder on rather than doing our own thing.
My first slide.
Thank you very much.
Second slide. So we already saw Adnan gave a nice overview of the ChEBI schema. And I'm going to focus just on the relationships between chemical entities and their roles. And so here are those two kind of things written as queries, and then using this relation ontology role. I'm going to put a big asterisk for the whole thing that I'm about to discuss, that the notion of roles and has role in ChEBI are not exactly the same as BFO. And so I've linked a discussion about that for anybody who wants to know more. Let's try and table that discussion for right now. So inside ChEBI, there's all sorts of great stuff, like actual instances of molecules and the roles that they have. So here's an example of uranophane, and it's a thioredoxin reductase inhibitor. The interesting thing that's going on here, though, is we've got like this reference within our ChEBI role EC 1.8.1.9. This is like an enzyme commission class. And I found it's kind of funny that there's actually no relationship between this ChEBI role itself and the actual like entity that's represented by this EC code. And it'd be really nice to have these relationships, like this role is a small molecule inhibitor of this, class of enzymes. Even further, kind of in the ontology world, when we know we've got a class of enzymes, it'd be nice to have all of those enzymes that are actually part of that class, like, for example, the human thioredoxin reductase 3. And then even further, using sort of the tools that exist for ontologies or just simple like network-based reasoning, we can start inferring stuff like, hey, this chemical is actually an inhibitor for this protein. So now we've got ChEBI and UniProt. And this is the kind of stuff that really interests me because I like to build knowledge graphs based on top of all of these ontologies. And so the idea behind ChIRO and then CROG, both two kind of funny names for the same idea, is we should be keeping track of all of these roles within ChEBI and annotating what are the actual entities that they correspond to, whether they're proteins, pathways, biological processes, enzyme classes, protein families, and whatnot. And then, coming up with sort of a good set of relationships that go between the ChEBI roles and these entities. And also coming up with a couple of rules. How do you go from the combination of like the entity type, the relation type between the role and the actual entity? And then how do you pick what's the right relation ontology relation to connect all the subclasses of like the chemicals that have that role to the actual subclasses of the thing that it's an inhibitor of? So how do we sort of infer directly inhibits from sort of this has role, is and then subclass chain? Okay, so yeah, we had to basically start by curating all this stuff. And so we had to think of what are the different ways that we could curate this. And so here's kind of a conceptual hierarchy of all the like kinds of roles that are existing within ChEBI that I found just looking through it. Unfortunately, not everything's organized this way, so it might be an interesting thing to add to ChEBI later, but you can find those examples of chemical modulation, protein modulation complexes, just like I mentioned before. And there's all sorts of even more interesting information, like if things are antagonists, agonists, whether they're activators or inhibitors. And when you talk about pathways, they call it regulators, but same idea. And if you're a chemical that's treating a disease, it's maybe like an antidote if it's for a toxin, or maybe you've got a chemical that kills a certain kind of virus, and then it's an inhibitor of the whole organism. So this is what that curation sheet kind of looks like. TSV, super simple, using really high quality standardized prefixes and identifiers for things, keeping track of the names, the kinds of modulations, the protein types. So the combination of modulation and entity type, is used to pick what's the relationship later, and then the targets. So what does that look like kind of in the end? We've got 836 of these manually curated entities within ChEBI that were roles that now have something attached to them, like that's in another namespace. And then when you sort of do this inference, you get tons and tons of extra relationships following these hierarchies, both of the subclasses of the chemicals and also subclasses of the target types, if there's something like a protein family or protein class. Important thing about all of this stuff is that the code and the data are available for everybody. There's no messing around with stuff being kind of closed. You can get this, you can add a row to the TSV and have GitHub Actions regenerate all of the artifacts. All the data is standardized with the bioregistry using like a very principled approach to making sure that prefixes and identifiers are standardized. It automatically creates all sorts of exports in like OBO and OWL and BEL and for Indra. And then it gets, auto archived to Zenodo. So there's like a lot of like reusability when it comes to this. All right, that's kind of it. It's a good place to start. There's sort of a preprint on this. We kind of have to resurrect this because we did it maybe 2 years ago at this point. So if you want to read a little bit more, you can follow that. You can always ask questions on the issue tracker that's linked here. So yeah, thanks for listening. So I've got to say thanks to like Ben and Klaus on my team and Laura and Peter, who are like sort of the heads of the laboratory systems pharmacology. And again, big thanks to Nicole and Chris, who were helpful in doing all of this and helping me to get oriented with the ontology aspect of it.
So I'm going to be talking about a proposed semantic schema for chemical entities. I'll get to exactly what I mean by semantic schema shortly. But just to scope this and put this in the context of some of the other great talks that we saw today, by chemical entities, I'm really talking about things at the level of atoms and above, up to the level of kind of like either equimolar or complex mixtures, but excluding more complex biological entities. And specifically talking about how we represent the entities themselves, their relationships between them, how they're connected in partonymies, and their various different properties. So of course, there's a number of existing databases and ontologies that all seek to represent chemical entities. There's a number of different machine actionable representations of these. There's as well as ChEBI, which we heard about. Chemical representations also make their way into a number of other biomedical and clinical ontologies as well. There's databases, of course, such as PubChem and Campbell. But even these kind of like dividing lines maybe aren't as neat as they seem. Within the OBO world, we think of ChEBI as an ontology, but the ChEBI developers think of it as a database that is converted into an ontology. But first, why ontologies? Why, given that we've got these great databases of chemical entities, why might we want an ontology? Well, ontologies have a lot of advantages. One of the primary ones is this relational representation, in particular, the ability to have a kind of multi-axial classification. So you can roll up your concepts to the level of granularity which you prefer. So, as a biologist, I might not really care so much about the different kinds of protonation states of a chemical entity, because these are maybe freely interconverted within the body anyway. So I may be interested in things at the level of citric acid or citrate, or the kind of conflation of those concepts. Using an ontology, we can kind of like roll up more specific concepts into the broader ones as well. And maybe one of the advantages that isn't as widely realized is the ability to use modern ontology frameworks, OWL reasoning, to automate the construction of these graphs. But unfortunately, many of the existing ontology representations don't take full advantage of this kind of ontology structure. So ChEBI doesn't have any OWL definitions, nor do any of the other chemical representations of ontological representations of chemical entities. And this means that we can't leverage a lot of automated techniques, such as automated classification using OWL reasoners, automated QC, also using OWL reasoners. And this isn't just a theoretical concern. This actually has practical implications for some of these ontologies. So I'll just quickly show you one kind of like common issue here, is that ChEBI is kind of like lacking kind of broader grouping concepts where we can conflate across these different protonation states. And instead, there's different hierarchies that are at a moment manually synced between them. And of course, whenever you have manual syncing, you have inconsistency. This is something that's kind of unavoidable, something we used to see in the old days with a lot of OBO ontologies before people switched to using OWL and reasoning. And it's something that can be tackled using kind of modern ontology frameworks. So the general approach I want to talk about here is something we've developed called a ChEMROF, Chemical Entities, Mixtures and Reactions Ontological Framework. So it's not an ontology itself. You can think of this as a kind of schema representation. It uses something called linkml to represent the schema. You can think of this like as JSON schema on semantic steroids. You can also think of it as a way of specifying design patterns for an ontology. So, I've shown a little section of ChEMROF on the right, the atom hierarchy. There's about 168 of these different modeling classes within ChEMROF, 183 different fields, and 33 different resources that have been mapped. Here's a little kind of hierarchy showing polyatomic entities and chemical mixtures, molecules, and so on. So just to kind of like give you a sense of some of the namespaces included within ChEMROF, we've heard from some of these today. And there's a little SSSOM file showing the different mappings between some of these concepts. But I want to show you, specifically a modeling class here. This is how we might want to model something like racemic mixtures or racemates. So the basic idea here is that this is a class that has different fields that represent the structure of this kind of class. So, with the racemic mixture, you may want to represent both the left and right enantiomers. And you also want to encode a way of saying that this is a defining structure for racemic mixtures. So we can see how we might represent this as data using the ChEMROF framework. So this is an experimental representation where we're treating kind of inches as curies or IRIs. So this is an example of showing thalidomide, and then the data representation. This is showing the turtle representation. It could also be in YAML, it could be JSON, it could be in a SQL database. Formally, this is an ALDL A box, but one thing we might be interested in is turning this into a T box, that's to say an ontology representation. So there is a way of translating this such that it will give you these OWL definitions. This is shown in Protégé. This is, if you like, the underlying RDF XML representation. This is how we might represent a racemic structure like thalidomide using this framework. And of course, once you have things in OWL, then you, with OWL definitions, then you're able to use things like automated reasoning to be able to classify things. So just to kind of like show that this actually works, using a kind of like a simpler part of the schema, I took all of the different kind of like representations of different forms of different periodic table elements, such as aluminium, and then kind of like structured it using ChEMROF, and then turn it back into OWL. And then you can see, just using an OWL reasoner, this entire hierarchy, maybe a little bit trivial, that you see on the left is classified entirely automatically. So there's no manual placing things within this hierarchy. It's all done automatically. So this really is intended to show a proof of concept of how we might start kind of like building our kind of like chemical ontologies to make use of reasoning. So it's at the moment this is not a kind of like product that can be automatically just used by domain scientists. It's more of a proof of concept at the moment. The GitHub repo includes lots of different kind of like exemplars of how this might work. We've got kind of like a partial ETL process that takes things from ChEBI Wikidata, turns them essentially into kind of these JSON-like structures, and then turns them back into OWL. But this is really intended to serve more as a kind of conversational starting point, both as a community standard for structuring knowledge about chemical entities, and as a framework for building kind of like chemical ontologies using reasoning. So I'm very excited to hear about development of ChEBI 2.0 today, and I'm hoping to talk to Adnam and others about how this can play into the development of ChEBI. So here's a link to the GitHub repo here. It's all fully open, pull requests welcome. You may also be interested, we're doing a little talk on using linkml for metabolomic standards at the MANA meeting coming up later on this month. And with that, hope I stayed on time and I can take any questions.
Awesome. Yeah, so hi everyone. My name is Matusz Kalasz. I work at the University of Bergen in Norway, and I'm a community co-lead and a maintainer of EDAM. And this presentation is on behalf of the whole global EDAM community of contributors. It was prepared together with the Lucie Lamotte, who is also in this workshop. She's a maintainer of EDAM working at the French Institute of Bioinformatics. Alban Gagnard, working at the University of Nantes in France, is our semantic web and linked data expert. And Hervé Ménager from Institut Pasteur in Paris is the EDAM community co-lead with me. And yeah, big thanks for the invitation and the possibility to be here. Yeah, so EDAM ontology, what is it? So it's a domain ontology of data analysis and research data management. It consists of 4 sections, including the topic, operation, data, and format. Now, more concretely, the topic section includes scientific and application domains, also some data acquisition techniques and some other key notions related to a research workflow as a whole. And examples could be drug discovery or electron cryotomography. The next section of EDAM is operation, and this comprises more concrete actions that can be performed with the data, usually producing some output data based on the consumed input. And examples of operations are molecular docking and mass spectra calibration here. Then the data sub-ontology includes concepts representing types of data on the semantic level, so to say. So independently of in which formats the data could be serialized in. So for example, peptide mass fingerprint is more complex kind of data, or it can be really simple data as a glycomap ID, which is an identifier in the database of glycans. And last, the format sub-ontology includes concrete and documented formats of data. For example, the SMILES notation or MMSIF macromolecular 3D structure format. There is a couple of relations which are maintained between concepts in EDAM. For example, the identifier, which is a distinct subsection under data, could be an identifier of some other kind of data or possibly some other entities. Now, with respect to the usage areas of EDAM, EDAM has been primarily designed for finding tools and services, workflows, learning materials, standards, and other digital objects. Or to see it from the opposite side, for annotating digital research objects related to data analysis, data lifecycle in general, in order to make them searchable better. A special case of recording is recording provenance metadata, where EDAM can help documenting, for example, the performed processing steps or data acquisition technology, and make the data more understandable, searchable, and comparable in that way. I used to say that just like making cities friendly for users of wheelchairs makes them better for everyone, it turned out that making EDAM good for these first 2 use cases makes it also useful for things like tools and data integration to some extent, where we can think about well annotated tools and data that can be filtered in a better way when searching for something suitable, like such as suitable input data for trying to perform something. And one example is matching of inputs and outputs and operation that could even help with some semi-automated workflow composition results. So there has been some work on that. As any domain ontology, EDAM can be used for text mining, obviously. And last but not least, EDAM has been really helpful for scientists who were writing about their data processing, data analysis, and they needed to find the correct terms for that. And so, for example, such as writing a method section in an article or in a workflow documentation, which not necessarily is the domain of the scientists themselves. When it comes to usability with other ontologies, the idea is that EDAM should be usable together with other ontologies. It is maintained as a typical oboe and owl ontology with some additional hint of some standard semantic web vocabularies. EDAM is distributed under Creative Commons share-alike license, which is a weak copyleft. This means that modifications must be distributed under compatible terms. However, it allows inclusion in other work distributed under any license without any restrictions. EDAM links to various upper ontologies, including BFO, GFO, Biotope, Dolce. And I saw that there are more new ones that we probably should include as well. So that's very nice. And we hope that this could allow reuse in really kind of bigger variety of scenarios that require a common upper ontology. Where possible, EDAM tries to link to other ontologies and knowledge bases. So it's a matter of curation effort often, but ideally there would be as many links to other well-maintained ontologies and knowledge bases as possible. The development of EDAM originates from the open source community and is very much influenced by this origin. So the contribution model is very community-based, meaning that EDAM relies on contributions from experts who help correcting and correct and enrich the ontology over time. And to enable this process, we employ a set of tools and workflows, including standard tools like Robot and also some additional tools that we had to develop. And some of these tools support exploration and assessment of EDAM concepts more for the users or for maintainers. And others are more concentrated on the validation and quality control in general. One of such example tools is the EDAM browser, which is more on the end user level, but it's also very useful for maintainers and curators. And this is a homebrew visualization interface that tries to complement the standard interfaces such as OLS and Protege and BioPortal. It has some nice extra features, such as showing this the usage of a concept across a couple of resources. Hopefully we could add more resources that use EDAM here as well, as long as they have some API that we could include. Or another feature is to provide an interface where people can suggest changes to EDAM just by filling in a form without having to look into the whole file. And then did get GitHub issue generated. The next step would be to get a pull request automatically generated, and we're not there yet. We hope that some of the new developments in the OntoDev could help, so we'll have to see. So EDAM is deployed in really a large diversity of registries and databases and part of various standards within life sciences, but growingly also beyond life sciences. So for example, in geosciences and especially in various interdisciplinary domains. And to conclude, EDAM is developed in a participatory manner, assisted by a set of both standard and custom tools, and we very warmly welcome new domain experts and contributors. So among the to-do things, definitely better coverage of some more specific chemistry concepts related to the chemical data analysis and data management. That really would be nice. Yep, that's it for me. Thanks for listening.
Okay. My name is James Overton. I'm not a chemist in any way. I specialize in scientific data integration, and I've been doing ontology development for more than a decade. And I'm deeply involved in the tools and infrastructure around the OBO project. And I'll talk later today about Robot and some of the other tools that we've got going on. But for this presentation, I'm going to talk about the Ontology for Biomedical Investigations, which I've been involved with for over a decade. So OB is an OBO ontology. It's about 15 years old, and somehow we've managed to have weekly calls for those 15 years, at least 50 contributors to the repository over that time, but we've never ever been directly funded. So OB is a community project, and that has lots of advantages and lots of disadvantages. As you can see, we have many thousands of commits. We started in SourceForge back in the day, and now we have a GitHub project. OB has always been OWL native and not based on OBO format. And we built it around BFO. And projects like the Information Artifact Ontology started inside of OB and then branched out into its own project. There's been many other projects that have kind of started outside of OB and then been merged in. OB uses imports from other OBO ontologies and reuses them extensively, probably maybe more than any other OBO project, which causes benefits and disadvantages. Here's a couple of our papers. Here's a diagram showing how we're fit under the orange BFO terms, the purple Information Artifact Ontology, the blue are the OB terms, and then the red ones are other OBO terms, such as ChEBI, molecular entity, for example. And we are built around the notion of an OB investigation, which is a kind of planned process with the study, design, execution steps. And in this version, you can see that the study, design, execution tends to start with specimen collection of a material entity, which might be processed into some kind of process material. And then we do an assay on it, and then we shift from material world into information world to get a measurement datum. We may do a data transformation on it. Then we may do some kind of analysis, drawing a conclusion process based on that. And to get more, this is the classic OB assay diagram where we have a mouse in the material world, and then we take samples from it. We use a device to do a measurement on it. And then we shift over to information in the information world. And then here's yet another diagram. Here we're measuring John's mass. So we have John on the left here, and then he's the input to a mass measurement assay, which has a datum, and then it links up to our value specification approach with units and numbers. So you might ask, why have all these complicated classes? And the key goal is for integration of data across many different data models that people have in different fields. And so we can get into a lot of detail, and then we can zoom out to much less detail. And so we're trying to hit all these different levels with the goal of driving data integration. When it comes to chemistry specifically, OB has always used ChEBI. We import more than 100 different chemical terms. We shove them under molecular entity, and we don't keep much of the ChEBI structure, so our list is quite flat. And then we reuse those chemical terms in many different assay definitions. So here's in OLS, we have our BFO top level, material entity, ChEBI molecular entity, and then underneath we have many different chemicals, and they're usually here because we're using them in some kind of assay definition. And assays are really the core of OB. We also use a bit of CHMO, and Colin talked about it earlier, and Colin was completely right that it can be hard to get stuff into OB, and I want to talk about that in a minute, but it's been a bit difficult. So CHMO builds on top of OB, and so we wanted to adopt these terms, which are kind of more general than CHMO, but we couldn't easily just re-import CHMO into OB, and at the time we wanted to do this, CHMO was not seeing a lot of development. So we tried this adoption strategy, which didn't work very well, and it's a problem. We use template-based development for a lot of things, robot templates. There was a long transition period where we adopted 1,000 assays into our assay template. And I'll show that to you in a second. The template consists of a bunch of annotations, text, and then a bunch of logic. And I'll skip over to this in like a Google Sheet. So for example, here's the assay template. We have CHMO assays. We have a whole bunch of different like annotations with the textual definitions and all those things. And then we move over into these logical columns where we have, for example, subclass relations to microscopy assay. Maybe we specify device, we specify evaluants or analytes, which often come from ChEBI in one way or another. I'm going to scroll down and find some of our more recent, like chemical clinical chemistry assays, where we're talking about like venous blood specimens, and then we're taking chemical terms and saying that's what we're measuring inside those things. Then we have output columns, and now we have target context columns, target entity processes that we're trying to measure, and then the context that it's being measured in. And so by putting everything into a standardized template, we do get a lot of power, but it is a fairly complicated template. And I was asked specifically to talk about the future of OBI and kind of lessons learned. We're pushing more and more into templates. So easily more than half of OBI terms are in templates now, but we want to do more of that because it's easier for people to contribute. We want better COB integration, and to some extent that involves giving up OBI terms like planned process. It's too general for OBI. It should be in a more shared ontology across OBO. And then we want better chemistry integration kind of through COB. And we're working on better qualitative, quantitative data modeling and better use of units, but I'm running out of time. The lessons I would say are the biggest problem for OBI is scope. So we've seen lots of little projects kind of branch off of OBI and then struggle to build critical mass and then die. Or we've seen lots of little projects start separate from OBI because they were funded by some short-term grant funding mechanism, fail to integrate with OBI, and then die. And so the consensus building process in OBI is slow and it's painful. But the fact that we've had this community that has lasted for more than 15 years is a win for OBI. It's the thing I'm most proud of. And so if there was one lesson learned, I would say that is it. So thank you for that. I am happy to take questions in our brief period or just contact me by email.
All right. Hi, everybody. My name is Michel Zmotzi. I maintain an ontology called the Semanticscience Integrated Ontology. This ontology is a kind of a general purpose ontology. It consists of an upper level as well as some elements of mid-level and domain level specific concepts and relations. But I think one of the major aspects about it is that it has sort of fundamental types to organize knowledge across different domains, and also a set of reusable relations across those domains. So the idea is that from a data integration perspective is that regardless of the domain, whether it's chemistry, biochemistry, or geosciences, there are basic kinds of entities in those domains that we generalize to, and then we can describe them in a very similar manner. You have seen, and there are many other ontologies that will be much more specific in terms of its domain coverage. But here we try to cover a little bit of everything. We use a set of simple design patterns to guide users into what kinds of representations would be useful in terms of objects and processes and their attributes, and quantities and informational aspects about them, and try to connect those through the set of relations that we have. And we are responsive to domain coverage requests where necessary, but often we will point people to ontologies that specialize in those if they exist, and otherwise we will add it to our ontology. So the project started in sort of late 2009, we published this paper in 2014, and we've been doing sort of one-off updates as time passes. So it's a pretty stable ontology. It was designed with a sort of a fundamental idea about how to represent objects, processes, and their qualities. And this sort of shows you a basic graph about how processes have themselves as parts, objects have themselves as parts, and then objects are participants in processes. Objects and processes can have attributes. Some of those attributes include capabilities or roles, and these are kind of like context specific, and then they are realized in particular situations or processes. So that's a very simple sort of like, I guess, paradigm for knowledge representation. And so the taxonomy sort of follows these basic fundamental types and then specialize from there. There are representations for space and time and information. And one of the key parts of the ontology is that there's actually only one data type property, which is called has value. And that means that any content, any digital content that you want to associate with an entity needs to instantiate a kind of class of that information, whether it's, for instance, it's a title or a description. or any other, smile string or whatever it is. These are all informational, and then they can be associated with the entity of interest. So it's a very general knowledge representation. You don't have hundreds or thousands of data type properties, you have one only. And so, what we have is an ontology with about, 1,600 classes, 211 object properties. Most of those are so about half of them are inverses, and a single data type property. So it's quite easy to navigate or to understand sort of like the basic fundamentals of the ontology, and to navigate through its structure, to identify both the types that you are interested in, as well as basic and independent or orthogonal relations to use to relate these things together. So we sort of pride ourselves in having very early on defined, this rich set of relations, and we try to describe the concepts with axioms. And so that means that as you navigate through the hierarchy, not only do you inherit the kinds of descriptions that exist for the parent terms, but at the extent possible, we try to define and sometimes fully define concepts in the ontology. And that's really useful from a data integration and knowledge representation reasoning perspective. That means that when you map these concepts to data in a database, then you can reason about them, and potentially you can classify and realize their types, more specific types than were stated in the data themselves. There is, as a biochemist myself, structural organic chemist, I have spent a little bit of time also defining types that are relevant in the chemistry domain, and you'll find them in ChIRO. But of course, as part of this series, you know that there are many other ontologies that go to much greater depths. But the point is that there's compatibility, I assume, between these and other types of ontologies, and that we can use them together. As I indicated, sort of a guiding light is these ontology design patterns. These are, we have a few different sort of, reusable patterns that are often used across domains. And this includes sort of, mereological relations, collections and membership, provenance, scientific investigations and measurements, and also sort of basic biochemistry descriptions, biochemical descriptions. And so this is really helpful for new users to sort of say, well, how do I describe something? Like, how do I do a measurement? And what are the entities and relations that are involved in that? And how are they constrained in some ways? And these patterns sort of like came out very early on. And I'm very excited to see that there are many new technologies to formalize these kinds of design patterns and schemas. And I think that's one of the things that we'll be looking towards doing. So ultimately, the ontology is useful to describe knowledge graphs. We use it primarily in biomedicine, but it can also be done in a chemistry context. And that's really that for all the different kinds of things that you have in your world, there are basic relationships that are going to relate these things together and allow us to describe them, and also to represent the data that we have in our databases and stemming from our experiments. And this is, I think, one of the strengths of the ChIRO ontology. All the entities are dereferenceable, so this is really good from a linked data perspective, and also from a distributed database perspective and federated query answering. And so many projects make use of the fact that we publish computable descriptions of our entities on the web. ChIRO is used in a number of different projects, including Bio30F, which is a big life science data integration project that we run. It's used in the European Joint Disease, Rare Disease Program, and at the EBI and CBI. And other projects have also made use of various parts of ChIRO that is relevant for the tasks that they have. Lots of people have contributed to this project over time, and basically any time that we get somebody who gets on the mailing list and says, here's what I'm trying to do, how do I represent it? We have them as contributors because they sort of like help us think about different domain aspects and domain representation problems, and this ultimately either leads to increased coverage in the ontology or, again, a description in terms of a design pattern. So we welcome engagement from that perspective, and we certainly like to work with the chemistry community towards that. The ontology is available by Creative Commons by attribution, and it's a free and open source project. Thank you.
So I'm going to be talking today about bioschemas. So bioschemas has a bit of a different focus from the rest of the ontologies that we've been discussing today. So most of the ontologies today have been focusing on how to accurately represent the chemistry. We're more about how do we make the chemistry data sets more discoverable on the web, and how do we exploit search engine optimization techniques to do that. So here is a quick overview of bioschemas and what we try to do. So what we have here is the Guide to Pharmacology page on a set of ligands. And we, as humans, we can read and interpret this page, but this is not interpretable to the web search engine crawlers or other people harvesting that data. So the suggestion from the search engines is to add in some markup. So this has been widely exploited for making hotels more discoverable, air flights, and so forth. And so we're looking at how can we do this for the life sciences. So we add some interpretation into the page that allows some indication of what is this page about. And in this case, we've got a protein, we've got a molecular entity, and we've got some basic information about that is allowed to help people search for this information. So I'm going to represent that with the bioschemas logo, just for convenience on this slide, and show where this could then actually be potentially exploited. So one possible route of exploitation is through the search engines themselves. So they use this already for dataset search. Another possible route of exploitation is through community registries. So ourselves within the life sciences community can exploit this markup and reuse it in our registries to develop aggregators and also additional services on the top of that. And then more general knowledge graphs can be constructed on top of this as well. And I'll show you in a minute how we're doing this with the OpenAIRE research graph. So as I said, this has originally come from the idea of integrating with schema.org. And schema.org is a lightweight vocabulary of terms for describing resources on the web and has very much a focus of products, e-commerce, and locations. So we have been extending schema.org with some types to represent biological and life sciences resources. And there are roughly 792 types in there. So these are the things that can be talked about, and 1,500 properties. So these are what we can say about those. And we now have 6 life sciences types in there, including biochem entity, with various properties that allow us to describe that biochem entity from a search perspective. Now, this has already been exploited by Google for dataset search. So there is a dataset type in schema.org. Now, the challenge here is the dataset type has something like 120 properties on it. And it's challenging to know which of those you're going to actually use. You're not going to want to sit down and use all 120, and not all of them are necessarily relevant. So, for example, does a dataset need to worry about whether it is family friendly or not? That's more to do with films and books and things. So there is a profile that has been developed to identify the sort of 10 recommended properties that you want to use to describe your dataset. And that is what Google used for their dataset search. And what we want to do in the life sciences is predominantly provide these profiles, these common usage approaches of these schema.org types. But to enable that, we also have to have schema.org types that are relevant for the life sciences. So we are extending schema.org with the life sciences types that we need as well. As I say, 6 of these have already been merged into schema.org, and we have many more in development. Our usage guidelines recommend about 6 minimal properties, maybe up to 10. And this is because people are lazy. We don't like to do lots of markup in our sites, but 6 to 10 is about the sweet spot of what people will sit down and actually implement. Now, we've seen many, many good ontologies presented today, and we don't want to step on your toes with this because our focus is very different. So our focus is very much about the search. So what's the terms you need to search for a data set or a particular item within a data set, rather than how to model that accurately in the biology or the chemistry. So at times we did go down that rabbit hole and try to get into the details of this, and we realized that this wasn't actually what we needed. But bioschemas does help with making your data fair. So it gives it global identifiers, it's a community defined model, it's indexable by the search engines, it gives us interoperability as well through common data representations. And this is being widely used as well. So there are 88 sites with bioschemas marked up in it. Across these 88 sites, there's 175 profile deployments, and we reckon there's over 80 million pages with this markup within it. And we've been trying to exploit that markup. But first, I thought I would just focus a bit on where it's being used within chemistry. So within chemistry, we have two types predominantly. So we have chemical substance and molecular entity, and these are inspired by ChEBI. And these have been deployed by the resources that you see on the left. And the example here is from MassBank. Okay, so we've got a chemical represented here, and then that is represented within the schema.org, the biomolecular entity type, and this can be extracted by search engines. I'm just going to skip over a slide. Or two. Okay, sorry. Should have. So what I wanted to talk about was how it's being exploited. So bioschemas, it can be exploited by the search engines itself, and this will give you the rich snippets that you commonly see when you're searching for movies on the web. We can also use it, or the search engines are using it to power the dataset search, which is what you see in the top right-hand corner. As I said, we're using it within the bioschemas or the life sciences community to power registries such as TESS, IDP Central, which is a dedicated resource for intrinsically disordered proteins. And so we're populating that using bioschemas markup from the sites, aggregating it together and forming an aggregated view over all of these resources that are available. And this allows you to search specifically for the proteins that are intrinsically disordered. And there's no central resource at the moment that would allow you to do that. And the other area is in the OpenAIRE research graph. And the idea here is that OpenAIRE would be able to extract the markup from the various sources, feed it into their research knowledge graph, and then that can be used to interlink and search across, so adding value to other services. So in summary, bioschemas is about adding machine readable markup, a lightweight description of your resource within the web page so that it can be exploited by others. So it's openly extractable and reusable. And our approach is to extend the search engine optimization vocabulary of schema.org with life sciences terms and concepts. And now this isn't the work of just myself. This has been a large community, and we're always open for people to come and join us. So we have a community call once a month on the 4th Monday of the month. The next one is the 26th of September. And we'll also be at the Biohackathon working out how to better exploit the markup that are in resources. I'll finish there for now.